Hi, I'm Mr. True. In this video, we're going to be talking about inverse variation and doing a little bit of comparison with direct variation before we get to our three examples. Now, inverse variation is when you have the product of two variables and they're equal to a fixed constant. If we take this equation and solve it for y, really common design of course, we get y equals k over x. Now, in inverse variation, neither the x variable or k, the denominator, or the constant of variation can equal 0. We can't divide by 0. Graphically, that's when we usually get vertical asymptotes, and that's where the function is undefined. And our constant cannot be equal to 0, because then we kind of really wouldn't have a problem, and it wouldn't be inverse variation. It would just be, well, y equals 0, a horizontal line. K is our constant, and it is equal to the product of the other two variables that are in the problem, or just the two variables in the problem. X times y is equal to k. So this is a good formula for describing how you find or what k is equal to. It's the product of x and y. Some word problems probably would be better set up that way. However, we very often work with equations where, of course, it's y equals, blah, 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 or y in terms of some other variable. And in that design, this y equals k over x, we read that as y varies inversely as x, or y is inversely proportional to x. So as soon as you're reading a problem and it's, blah, 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 something is inversely related or inversely proportional or just inverse, has an inverse relationship with some other variable, why don't you just stop right there and write y equals k over x, because that's going to be the design that you're going to work with for the problem, or of course, x times y equals k. And it would probably be a nice idea, I would think it's good, to maybe not even worry about writing it as y equals k over x, because what is x and y, but instead use the variables, the full words of those variables that are in the problem. That way you can keep it in context, what number goes where and whatnot. Now, direct variation is y equals kx, or y divided by k is equal to x. So when you have direct variation, it's the quotient between y and x, or y divided by x, that sets up that constant, as opposed to inverse variation where it's x times y is equal to k. If we look at this form of this equation, the direct variation where it's y equals, y in terms of, y equals kx, you might recognize this as y equals mx, and then of course there's no constant, but it's 0. And y equals mx plus b, or y equals kx, that is the equation of a line. So over here, I've got just a couple of quick graphical representations of what direct variation is. It's y equals a constant times x. So basically you're looking at a line with a y-intercept of 0 and a slope equal to k. Now, most of these problems do have k values that are equal to or are a positive value. So we kind of get into a bad habit of saying, direct variation is when one variable gets bigger, so does the other variable. But that's only the case when we have a k value which is positive. If we have a k value which is negative, and I included one of those examples when I did my video on direct variation, it is possible to have a negative slope in direct variation, or in other words, as one variable gets bigger, the other one gets smaller. So you might be able to get away with most of your problems thinking that, oh, for direct variation, as x gets bigger, so does y, and with inverse variation, as x gets bigger, y gets smaller, but that's not really correct. That would only be acceptable to, well, it's never really acceptable, but it would only consistently get you right answers if your textbook happens to always give you problems where the constant k is positive, but does not have to be. So what is the difference between inverse variation and direct variation? I got the labels over here, by the way. Direct variation is a linear relationship. It has a graph which passes through the origin. There is no plus or minus b, it's just y equals kx. So you're looking for a linear relationship that passes through the origin. Whereas indirect variation, and again, if k is positive, as x increases, y decreases, but that's only when k is positive. I've only done the example graph for when k is positive, by the way. But you have y equals a constant, I've just picked one out of convenience, over x. Now when you graph y equals 1 over x, you have a vertical asymptote where the denominator is equal to 0 because it can't be canceled out. So we have this vertical asymptote, and the graph kind of swings down from that vertical asymptote and tapers off to the right. And you can see here, when k is positive, my y values are decreasing when my x values get larger. And we don't often deal with x values that are negative, especially with a lot of word problem settings. But again, here we have x is getting larger and y is getting smaller. But we can see the graph is not linear. We can see the graph has a vertical asymptote where direct variation does not. And again, k can be either positive or negative, though that negative possibility for k is largely ignored in many textbooks, and that's why some students will incorrectly, even some teachers will incorrectly say direct variation is when x gets bigger, y gets bigger, and when we have inverse variation as x gets bigger, y gets smaller. Those summary statements are only good when your constant is positive. Now, before we get to our full examples here, one real-world example, and we're going to finish with an actual word problem in this video, but one real-world example is traveling. Now, depending on which variable is fixed, this could be direct or inverse variation, but we're going to talk about motion problems in the form of distance equals rate times time with a question of fixed distance. If you need to travel 150 kilometers, the time required would vary inversely with the rate. If you have to go 150 miles, which is distance, that's equal to rate times time. So, you know, if you say travel faster, it's going to take you less time to get there. If you travel slower, it's going to take you more time. So, in this example, k is positive. So we see where as one variable gets bigger, the other one must get smaller. Again, that's only a good summary statement if k happens to be positive for your problem, and then it usually is. If I want to write, let's say the time it takes you to get to your destination in terms of the speed, well, I would divide both sides by r and get 150 over r is equal to time. Again, you can see how that looks exactly like our textbook definitions for inverse variation. Two variables being multiplied together to give us a constant. Rate times time is equal to that constant distance that we need to travel of 150 miles an hour, 150 miles or kilometers. Yeah, kilometers. And y equals k over x. We can solve that for t and have time in terms of the rate at which you're driving. It's time equals a constant over a rate. Again, just validating that this design, distance equals rate times time, when distance is fixed, would be an inverse relationship. R and t would be inversely related to each other. Let's get to some examples. So over here we have if y is inversely proportional to x and y equals 7 when x is equal to 4, find x when y is equal to 18. So as soon as you read inversely proportional, then decide whether you want to set up your equation as xy equals k or y equals kx. It really doesn't make any difference. They're both, inverse proportions. So it says that when y equals 7 and x equals 4, when y equals 7 and x equals 4, find x when y equals 18. All of these problems in a textbook, unless it's some really ridiculously hard one at the end of the section, all pretty much set up the same way. They give you enough information in the first part of the problem to figure out what the constant of variation is, and then they ask you a second question, and that's really where you want to use the equation. It's kind of like you find the equation first, and then you use it in the second half of the problem. So when they say here, and x or y equals 7 when x equals 4, that piece of information is there to help you find out what k is and thus know what the equation is. So we have, let's just use this one. We have y equals 7, so we're going to plug 7 in here. We're looking for the constant of variation when x equals 4. Oh, okay, so that's pretty simple. X is 4, y is 7, 4 times 7 is 28. So that means that our constant of variation is, 28. So I can write the equation as either y equals, take the k out and plug in 28, or I can write x times y is equal to 28. Whatever you feel best suits your problem. So it says find x when y is equal to 18. Now it says find x when y is equal to 18. If I put that equation into here, find x when y is equal to 18, then I'm going to solve this equation by multiplying both sides by x, because you can't solve for a variable when it's in the denominator. And when I do that, I get x times 18 is equal to 28. The same thing I would have had here if I had used this form of the equation in the problem. So, using y equals k over x caused us a little bit of extra work if you wanted to start the problem that way, or if you had started the question off with xy equals 28, we would have saved one step in the solution. Now, it just depends on the way the information is given to you in the problem. One format is not necessarily that much greater than the other, but we do have x times 18 is equal to 28. So we're going to divide both sides by 18 and get x is equal to, now these numbers, let's see, they both are even, so I can divide a 2 out of the numerator and denominator and reduce this fraction. 28 divided by 2 is 14. And 18 divided by 2 is 9, so x is equal to 14 over 9, or as an improper fraction, if you want a mixed fraction, there is 1, 9, and 14, and 14 minus 9 is equal to 5, so the remainder is 5, so we have 1 and 5 ninths, or of course you can write that as a rounded off decimal, but if you want an exact value answer, we want 14 over 9, or 1 and 5 ninths as your final answer. On our second example, we have y varies inversely as the square root. So a little bit more complicated here. And of y, and, okay, before we even worry about the numbers, let's get the problem written out, or the format written out. Y varies inversely as the square root of, x varies inversely as the square root of y. Now, I think it's going to be a little bit simpler again if we use the x times y equals k format, and x varies inversely as the square root. So we're taking the square root of y. So we're going to have x times the square root of y is equal to k. Now, let's go ahead and stick with that and try and then go to the next part of the problem, which says, and x is equal to 24 when y is equal to 49. So they've said the design of the problem, inverse variation, so two variables being multiplied to give us a constant, except we are doing the square root of y, not the regular, just y. And x is equal to 24 when y equals 49. Well, we have an equation here with three variables, and we need the constant. That's why that information is given to us. So x equals 24 when y is equal to 49. And therefore, when that information is given, what is k? Well, the square root of 49 is equal to 7, so we have 24 times 7 equals k. And what does that make k? Well, 2 times 7 is 14, so 20 times 7 is 140. And a little 140 here. And 7 times 4 is 28, so 140 and 28 is 168. Okay, so we have k using the information given. So we have our equation of x times the square root of y is equal to 168. Find x again when y is equal to 64. So find x when y is equal to 64, so we're going to take out y, plug in what it's equal to, that's 64, square root of 64 is 8, so we have 8x is equal to 168, or x times 8, is equal to 168. We want to undo that multiplication with division, so we're going to divide both sides by 8 and get x is equal to, let's see here, 16 divided by 8 is 2, and then 1. So the final answer is x equals 21. I wrote these examples with this format of x times y equals k because they were ultimately asking us for x and not asking us for y. So I don't want to use an equation that's set equal to y, where it's y equals blah blah blah, when y is being given to us and we need that variable on the other half of the equation. Again, with the way these problems are set up in their wording, that would have just added one extra step in our problem. Let's do one more example that deals with, it's really not much more complicated than these, but it looks like a word problem, and that just alone scares some students. Last example, and it's a word problem, always a little bit scary. A sprocket gear 10 inches in diameter is connected to a gear of 3-inch diameter. How fast does the smaller gear rotate when the larger one rotates 248 revolutions per minute? Now, one reason I'm doing this example is, of course, anything mechanical that's not purely electric. Almost all mechanical gears, gears inside of an engine, wheels on a car, a bicycle, anything mechanical that's just not just pure electronic like my camera here is, well, even it probably has some gears on the inside of it. And so when you think of a bicycle sprocket, some bikes have, 1, 2, or even 3 sprockets in the front. Most have a couple, 1, 2, 5, 6 gears in the back, whatever. And you can move the chain around, which is going to change how fast you have to pedal for how fast the bike is moving. The bigger that front sprocket is compared to the back one, as you make one rotation of your pedals, you pull a lot of chain through there, which is going to have to go around the back sprocket. And if that front sprocket is really, really big compared to the very small one in the back, a little bit of movement here in the front is going to be a lot of rotation in the back. Or maybe you're going uphill and you change it to a gear which makes that sprocket smaller, or moves the chain to a smaller sprocket. If this front gear gets smaller, then for every rotation of the front gear, the back one is going to turn less. Or in other words, you're pedaling faster and yet you're still going the same speed on the bike. So it's a good question that has some real-life applications. And again, linear and angular velocity and pre-calc and trig uses this type of problem a lot. So enough babbling, we haven't studied that yet, so I need to give you a hint. Revolutions a minute times circumference is equal to your constant of change. And we must be given some information or enough information in this problem to allow us to find k, the constant of change. Well, we have for the larger gear, we have that it's rotating 248 revolutions per minute. So what other information do we have for the large gear? We have that the large gear has a 10-inch diameter. So we have how fast the large gear is rotating, revolutions per minute. We have the circumference, or can find the circumference for the large gear because we know how big it is in diameter, and that's going to give us a constant of change. So we have revolutions per minute. Well, that's equal to 240 or 248. We have circumference. Well, the circumference of the front large gear, the information we're given about this rotation, is 10. The diameter is 10. Well, circumference is equal to either 2 pi r or diameter times pi. So our diameter is 10. We multiply that by pi to find the circumference of the large gear, and that is equal to our constant of change. So we have 248 times 10 pi is 2480 pi is what k is equal to. So we're given enough information to find out, again, that constant of change so that we can actually write out the equation, which is revolutions per minute times the circumference is equal to k, which I was about to write k, but we now know it's 2480 pi. Okay. So now we're going to move on to the small sprocket. We've used all the information we can from the large sprocket, the 10-inch diameter sprocket. Let's move to the one in the back. The one in the back has a 3-inch diameter. So revolutions per minute its diameter again is 3, so its circumference is 3 pi. is equal to 2480 pi, the constant of variation that we found from the front sprocket. We want to find revolutions per minute, how fast the back one is rotating. So revolutions is equal to 2480 pi over 3 pi. Of course, those pi's are going to cancel out, and just for practice sake, instead of just typing this into our calculator, 2480 divided by 3, 3 times 8 is 24, which gives us a remainder of 0. Carry down the 8 for 80. There's 2 3's and 8, so 2, 8 times 3 is 6. Bring down a 2, because 8 minus 6 is, 2 of course. 3 times 20, well, let's see here. How many 3's are in 20? 3 times 7 is 21. 3 times 6 is 18, and we have, again, a value of 20. And since we just had a difference of 20, now we have another difference of 20, and we're going to have another difference of 20 because we're going to continue doing 3 times 6 is 18, and 20 minus 18 is 2. So we're going to get 826 and 0.6 repeating, or 826 and 2/3 revolutions per minute. Now with this word problem, you might notice I never wrote y times k equals, or y times x equals k. If you keep the full language in there, then when you're done, you don't have to think about, okay, I just found out what x and y was. What was that again? And go back and read the problem and go, did I just find, distance or rotation or speed? What did I just find? Oh, if you take the time to write the full words out instead of just x and y, then when you're done, you will not have any doubt as to what it is you just found. It's not just a generic x and y, which really doesn't mean anything in terms of a real life problem. So, I'm Mr. True. Go do your homework.